I won't be talking exactly about what Earth is going to look like in 50 years. That's what Tom asked, and I don't mean to sell you under false pretenses, but when we started, let me get the pointer here. When I started this lecture, I thought, oh good, I'll go back and study everything and find out some good predictions, and then I realized that we are horrible as predictors. All the predictions I saw from the last 20, 30, 40 years about what the world's going to look like have been not just a little off, but horribly wrong. So I thought, well, I know the title's already been out there, but I can't do that. So what I'm going to do, important first is to acknowledge first Tom and the Brookhaven Lecture Committee for inviting me to give the lecture. All my colleagues, both here and far, who helped in one way or another, providing pictures, a lot of discussions with people about these topics. Too many to name personally, and if I left anybody off, I apologize. And also the atmospheric system research part of the Department of Energy, which funds my research on this. So I'm going to talk about the Earth today. We're here for Earth Day. Earth Day is Friday. And the Earth is a wonderful topic. That's where we live. I think of the Earth as being our landlord, and we are the tenants on that. And I want to talk about our relationship with the Earth. The Earth is about 70% water, about 60% of it at any time is covered by clouds. And we think of the Earth as vast. This is a picture taken of Earth from the International Space Station. And this is, whoops, pointer. This is the Earth on the bottom. It's just sunrise, the sun's coming through. This is dark outer space. And you can see that the thickness of the atmosphere is really pretty narrow there. And if we were to take the atmosphere, make it the same density as it is at the surface, it would be about 5 miles high. That's not very much. It's about equivalent to the thickness of a single coat of paint on an orange. The oceans are only about half that deep. The average depth of the oceans is 2.5 miles. Now, through our activities on Earth as humans, we have already impacted the atmospheres in many ways. We've changed the temperature, we've changed the composition, we've changed the hydrological cycle. We have changed the atmospheric dynamics. We've also changed the oceans, which are much vaster in terms of mass. We've changed the chemistry, the temperature, composition, fisheries in many ways, and I'm going to talk about some of those today. 2.6 million years ago, our geological epoch went from the Pliocene to the Pleistocene, and 12,000 years ago, it went from the Pleistocene to the Holocene, and now many scientists are arguing that we need another epoch, the Anthropocene, showing that the impacts we've had as humans on this. So we have left our mark on the geological record in many ways, and in millions of years, regardless of where we are, future civilizations, while there might be, can go down through the cores and find records to show that we were here. We have changed the planet. When I told a friend I was giving this talk, a friend here at Brookhaven, he said, oh, I heard a talk like that at Berkeley once, and I went up to the speaker later and said, that was a really good talk, but it was really depressing. And the speaker said, well, I have three versions of the same talk, and this was the most optimistic I gave. So my request is, don't shoot the messenger. I'm just a messenger here. Okay, so what does Earth look like in the future? That was supposed to be the goal, and that's what I worked really hard at. And Hollywood had a lot of ideas for this. Some of these were interesting, that the ice caps are going to melt and we're going to be living in an aqua planet, or we're going to run out of gasoline, or the Earth will freeze instantly. But I found some scientific inaccuracies in some of these, and even though they were, put it mildly. So even though these were clever ideas, I thought, oh, I'm not sure I'm going to buy any of those. So as I said, predicting the future is very, very difficult. Now, this is attributed to Niels Bohr. There's no record he actually said that or wrote that, but he's given credit for it. So if it's so hard to predict the future, what's our best guess? How do we do that? How do we project into the forward and see what's going on? So he actually did say this, or rather wrote it in a book 100 years ago. There's various versions now. But George Santayana was an essayist and philosopher at Harvard, and he wrote, those who cannot remember the past are doomed to repeat it, and condemned to repeat it. We don't want to repeat the past. We made some mistakes, and hopefully we've learned from them. So with that idea, we're going to take a little time travel here. Oh, sorry, missed a slide. So how do we predict the future? So scientifically, we have something called a hindcast. So this is made up data. Don't worry about what they are, but let's assume the red is measurements, and I have a time series here in temperature, but it can be anything, going back 150 years or so, and I have a computer program. That's what we do in science. If I can write a computer program that contains all the physics and science I know and simulate this same event, then I think I understand what's going on. So the green would be my model. So I'll start my computer run in 1870, and I won't put anything in. And if I can get it to match pretty much what the data does, then I say, well, I think I understand it then. I've captured everything that's going on in the real world in my computer code, and now I can take that and have some confidence that I can start it now and project into the future. So that's the idea. It's the best we can do. But just like in the stock market, past performance is no guarantee of the future. So with that, we're going to go back now 50 years. We want to look at what Earth's going to be like in 50 years from now. Let's go back 50 years in the past. So my first thought is the Wayback Machine, and a lot of you people won't know it, but those of my generation will. There's Mr. Peabody on the left and his boy Sherman, and he has this Wayback Machine, and I went to try to find one, but I think it ran on vacuum tubes or something, and it just was not feasible. So I said, okay, well, scrap that idea. So I said, Back to the Future, right? We've all seen that, but I think Spielberg gave the DeLorean to one of his kids or something, so that's out. I'm like, oh, now I'm struggling. How do we go back 50 years? And I'm like, okay, how would a young kid today? I'm in the 21st century, I'm trying to be modern, so there's an app for that, somebody told me. Pretty cool. Kind of expensive, but we take our app, put it on our iPhone, and we set the date to April 20th, 1966, and we're all gonna take a little stroll through memory lane, or some of us that have been there, take a stroll through memory lane just to see what the world was like then. 50 years ago on this stage right here today, Bernie Manowitz gave a talk. And you can see the luncheon was $3.25 for a buffet supper after this, okay? The budget of Brookhaven National Lab was $50 million in 1966. It's more than 10 times that now. It hasn't quite kept up with inflation, but $50 million. Very tough year personally. That's me on the right. I fell in with the bad crowd and had to do some time. But I've reformed. I paid my dues to society. How'd the world look population-wise? Upper left is US population. We weren't even at 200 million people then. We're at 323 million people now, and you can see there's been pretty much a steady rise since then. World population less than half the current rate. 3.4 billion people. Now we're over 7 billion. Dow Jones Index, on this date it was 951. Ending the year was 786, and you can see for the next quite a bit of time, we had a pretty steep increase, a little dip with the dot-com boom, recent recession, we're going up again. Just to kind of scale things, we're living down here economically 50 years ago, we're up here now. Culturally, Star Trek debuted on TV, that's probably the biggest thing for a lot of you. Good, Bad, and the Ugly was in the movies. Music, I had at first on my first slide like 6 albums. There were just so much great music that year. This guy named Jimmy moved to London and changed his spelling of his name and formed The Experience, and you know, it was all kind of history from then on. So I'm trying to bring everybody back so we all see what the world was like then and get a feel for that. Sports, this guy on the left finished his freshman year at UCLA and started being coached by John Wooden. The Orioles beat the Dodgers in 4 games, and that's with Koufax and Drysdale pitching. That's just amazing if anybody thinks about it. And my guess was that most people won't get this right. Anybody guess who that was? Lou Alcindor, very good. Kareem didn't exist till 1971, so this isn't Kareem, it's Lou Alcindor. Telephones were very different, and for you young people, this is the best picture I could find, but there's really a wire going to the wall, so it's not like you walk around with this and call. It was a very different world back then. And we had this cartoon, Dick Tracy, and he had this watch that he could call headquarters with, and a talking watch, I mean, how absurd can this be? There's no way that could ever happen. Okay, social issues. The 60s were a time of severe social unrest, civil rights, Vietnam, those were under Lyndon Johnson's administration, and those were serious issues, but the overriding spirit of the time, and looking back, I kind of remember this in my reading, I'd forgotten about it, is the threat of nuclear war. It was a nuclear buildup, it was a Cold War, and everybody was afraid that we were gonna have the bombs drop. So fallout shelters were public buildings, schools that would have food stocked under them that you would go in case the bombs fell. A lot of you probably remember these duck and cover exercises. The teacher would tell you, get under the wooden desk and put your hands over your head. So looking back today, I go, if the bombs fell, I'm not sure how much good that's gonna do, but when you're in 3rd grade, you do whatever the teacher tells you. Okay, how did our atmosphere look? I'm gonna talk about atmosphere, I'm gonna talk about water on Earth, I'm gonna talk about our relationship with other inhabitants, meaning animals. So the air was pretty bad in the 60s. Los Angeles and Southern California is kind of ground zero. Photochemical reactions forming smog. So smog forms from auto exhaust, and it forms from heat, and it forms from sunlight, and Southern California is perfect for all those. Plus they have a ridge of mountains along there that everything piles up and it doesn't get ventilated very well. See, these women are tearing their eyes. If you've been there in smog situations, there's chemicals that once they hit mucous membranes, eyes, nose, throat, they burn, they sting, and they're crying. It was really painful for that. Even going back to the 40s and 50s, okay, I don't think this was a staged picture. This was probably somebody wearing this. Smog was really bad in a lot of areas. This picture of me, believe it or not, I played basketball in a small college in a suburb of Los Angeles in the 70s, a little decade later. Sounds a lot more impressive than it was, trust me on that. I would go into the gymnasium, and you can see it's a 2-story gym. It was about like this, and I could tell if it was going to be a good day or a bad day just by looking at the ceiling and telling it was hazy or not. It was that bad even in the 70s. Now, you're all fairly smart people. You know this is before the days of Photoshop, so this is a real untouched photograph. Still, I would be incredibly skeptical on everything is not like you see it. It wasn't just Los Angeles. Birmingham, Alabama had a stagnation event. Total suspended particles, 700 micrograms per meter cubed. Okay, the current EPA regulations are you can only make it 150 once per year, and this was 700. Both coasts, New York City in the 50s and an Earth Day in 1970, the same thing. A lot of you remember this. The smog was incredibly bad back then. So our air was pretty bad. This is sad. This is our gloom. Okay, how did our water look? Potomac River flows through Washington, D.C. 85% of the people get their water supply from the Potomac. It's our nation's river. How did it look back in the 50 years ago? Oh, before that, let's go back a couple hundred years. John Smith of Jamestown was one of the first explorers to go through there. And this is worth reading. In 16th of June, we fell in with the river Potomac. And in diverse places, that abundance of fish, lying so thick with their heads above the water as for want of nets, our barge driving amongst them, we attempted to catch them with a frying pan. It's a little odd, I know. But we found it a bad instrument to catch fish with. Here's the important part. I highlighted this in yellow. Neither better fish, more plenty, nor more variety of small fish had any of us ever seen in one place swimming in the water. This was abundant in fish. And of course, they're not to be caught with frying pans. Well, okay, a frying pan is not a fishing net. That's his take home, but that's not my point. This was an abundantly productive place biologically. This was a beautiful river before we came and did things to it. So 50 years ago, open sewer, unsafe for swimming. 50 years ago, Lyndon Johnson called it our national disgrace. Severe threat to the health of anyone coming in contact with it, not swimming in it, not eating fish out of it, coming in contact with it. Okay, this is not good. But the really poster boy for bad rivers is the Cuyahoga in Cleveland. Some of you have heard of this. Very small river, it's not even 100 miles. It drains less than 1,000 square miles. Filthier than ever. Waste treatment lagoon, choked with debris, oil scums, floating globs of organic sludges. This doesn't sound appetizing. This is right through the heart of the city. Brown oily film, large quantities of black heavy oil, inches thick, grossly polluted. I think my favorite is one of these two. It oozes rather than flows. And the locals said that if you fall in, you're not going to drown, you're going to decay. Okay? I mean, this is horrible. We're living with this 50 years ago. Lower Cuyahoga has no visible life, not even low forms such as leeches and sludge worms. And it gets worse. A few years later, the river caught on fire. So when rivers catch on fire, you know things are bad, right? Not necessarily. It was a 5-page story on page 11. Okay, this didn't even make the front page as a major story. Why? Well, there were at least 10 previous fires before. The one in 52 burned for 8 days. The one in 1915 killed 5 people. This was kind of a regular occurrence. Okay, we had reached a point in our society where the rivers catching on fire was just something you take for granted. It inspired songs. Randy Newman had a song. R.E.M. has a song about this. So we polluted the air pretty bad. The rivers are pretty bad. This is gloom and gloomier. Okay, how about environment? How about our relationship with other inhabitants on the planet? This compound was prevalent, dichloro-diphenyl trichloroethane, or DDT. So DDT was a good thing. This is better living through chemistry. This wasn't a harmful chemical. Paul Mueller got the Nobel Prize for discovering the insecticidal action of DDT. Okay, it was contact poison against several arthropods. Arthropods are what? Well, here's a list of arthropods on the left and some of the diseases they transmit. Malaria kills 750,000 people a year in the world. It infects over 200 million. Yellow fever, dengue fever, Zika is the last one that I should have added. That's a recent one that's coming about now. Leishmaniasis, Chagas disease, typhus, and plague, all are tick-borne diseases. These are all things that DDT was designed to help. DDT was supposed to be a benign chemical. These are ads from the 40s and 50s from Time magazine. If you look on the right, you can get DDT impregnated wallpaper for your child's room. Protect him from these evil insects. Okay, DDT is good for me. Here they're spraying a girl with DDT. Okay, right in the back of the head. This was considered okay. Nobody saw any harmful effects here. And I remember these. This is Waco. This is a picture I found, but I remember these trucks. And I asked my mom last time I was back, I said, did I remember this correctly? She said, yeah, that was probably it. I was 4 or 5, and these trucks would drive down the road with this big blue cloud of smoke, and we'd want to go play in the ditches that went over, and my mom wouldn't let us. She'd make us come inside, and we argued it was safe, and my mom was smarter than we were. She said, no, you have to come inside. So we've forgiven her, but still it would have been really fun to play in the DDT track. But Rachel Carson in the early 60s, she was a marine biologist, wrote a book called Silent Spring on the effects of DDT. And she took her title from this poem by Keats. The sedge has withered from the lake and no birds sing. So she writes in the book, over increasingly large areas of the United States, spring now comes unheralded by the return of birds, and the early mornings are strangely silent, where once they were filled with the beauty of birdsong. Because she did studies and was taking surveys and realized that birds were dying rapidly. She talked about, like the robin, another American bird seems to be on the verge of extinction. That's our national symbol, the eagle. She wrote that just over 50 years ago. So we're talking about birds, possibly very common birds, being extinct. So those of you who knew me probably took bets as to how many slides before he starts talking about birds, right? Okay, that's just, I'm not gonna give a talk without working birds in. But birds are important. This is a canary in the coal mine, literally. And for those of you who don't know what the analogy, coal miners worrying about carbon monoxide and other things would take a canary down there. And if the canary's singing, everybody's happy. But if the canary starts falling on its side and laying on the bottom of the cage, you better get your respirator on because you know this is not a good thing. So birds are indicators of the environment. They live in the water and the air. They eat the food that's directly in contact with this. It will have pesticides run off if they're damaged and so forth. So birds are a good thing. They tell us what's going on. So how did bird life look 50 years ago? Bald eagle. In the lower 48, it's a bird only found in North America. That's the current range from Cornell Lab of Ornithology. 50 years ago, there were less than 400 nesting pair in the United States. Any guesses as to how many nested in New York? 1 pair. And it hadn't successfully raised any young. In the whole state of New York 50 years ago, there was 1 bald eagle nest. No young were born. That's not looking good. Osprey, look at some of these numbers here. It's a cosmopolitan bird, but between New York and Boston, 1,000 pairs in the 40s to roughly 10% of that in the 70s. Connecticut River Colony, 200 pairs to 12 pair. 300 pairs to 21, and all along Long Island, almost 500 pairs to less than 75. This is not looking good. The brown pelican, state bird of Louisiana, hadn't been seen in Louisiana since 1963. They were gone from the state. One more bird. Peregrine falcon, the most amazing bird ever to fly, in my opinion. I knew somebody who used to capture these and put rings on their legs so you could catch them again and see where they'd been, migration studies. He caught one in Greenland once and said his partner caught it on the Texas coast 10 days later. 5,000 kilometers, 10 days, and that's assuming it left at A, caught it. Eastern race was gone by 1964, totally obliterated. All of this from DDT. It's not just New England. It was Louisiana. It was the whole eastern seaboard. DDT was the cause of all these. Okay, things are looking gloomy. Gloomy, gloomier, and gloomiest, I think. So what happened? Oh, summary of the 60s, okay? A lot of social stress. We're napalming children. This is horrid. So how do you survive this? Well, you go to nature and look at birds and the beauty of wildlife, except there are no more birds. And even if there were, you wouldn't be able to see them because the air is so thick with smoke. You can't go swimming because you might catch on fire or decay, and mom won't let you play in the DDT truck. So the 60s really were not a pretty good era for, our environment. Our relationship with our environment was pretty bad back then, 50 years ago. But it kind of didn't matter because we all thought we were going to get totally obliterated by the nukes. And that was really the overriding theme at the time. So what happened? Earth Day is what happened. We did something about it. Earth Day was 50 years ago from the 22nd, which is Friday. It was originally on a Wednesday. And this person, Senator Gaylord Nelson, and this person, Representative Pete McCloskey, hired Dennis Hayes to do an Earth Day celebration. It was the first Earth Day. He was a Democrat. He was a Republican. This wasn't a political thing. It was bipartisan. And this is the New York Times on the next day. Roughly 20 million people around the United States went out for Earth Day. So we're here to celebrate Earth Day, and I think that was a wonderful thing. We should really celebrate, because there were some amazing things came out of Earth Day. It was a major changing point in our environment, or our relationship with our environment. So outcomes that are attributed to Earth Day, these just didn't occur temporally. These were directly a result of Earth Day and the public dissatisfaction with status quo, with burning rivers, with air that you couldn't breathe, with wiping out birds. Environmental Protection Agency was formed in 1970. For one time, it got all the regulatory agencies under one guise. Clean Air Act, Clean Water Act. DDT was banned in 72, Endangered Species Act in 73. Now there were Endangered Species Act before this, there was a Clean Water Act before this, but they really had no teeth. So when you say the Clean Water Act, you really mean the Clean Water Act of 1972. Same thing with the Endangered Species Act. It's the Endangered Species Act of 1973. All these were passed under Richard Nixon. Okay? So let's look at these. The mission of the EPA is to protect human health by safeguarding the air we breathe, the water we drink, and the land on which we live. And it had regulatory capabilities here. Okay, it made air quality standards. It could fine people. It could do things. Clean Air Act authorizes the Environmental Protection Agency to make national standards to protect public health and public welfare, to regulate emissions of hazardous air pollutants. You saw from the previous slides, you can pretty much dump anything into the atmosphere. This is the most successful bill ever. The benefit to cost ratio is $30 to $1. So it cost roughly, from what I've read, 0.5% of our GDP to do all the regulations, and with illness, lost work days, other gains to the environment, it was between $30 and $40 savings for each dollar we put into this. The second place bill was $2 to $1. So the Clean Air Act was the most successful bill ever, according to the EPA in a peer-reviewed study under George Bush Jr. Clean Water Act regulates the discharge of pollutants into waters. So remember the Cuyahoga, which had oil scums and everything, as long as you didn't impede ship traffic, you could dump anything you wanted into the water, basically. And the problem with both Potomac and the Cuyahoga is there was raw sewage going into it. There was oil, any kind of waste, as long as ships could still make it through there. DDT, that's a story that could be a whole lecture here. It's got a Brookhaven history. Dennis Puliston, who was working at Brookhaven at the time, Art Cooley, George Woodwell, Charles Worcester, and others, most of whom lived in Brookhaven Hamlet, sued the Suffolk County Mosquito Commission to stop spraying DDT in 1966. This action eventually led to banning DDT. Charles Worcester, whom I've never met, is giving a talk tomorrow night at Wertheim National Wildlife Refuge in Shirley on the founding of the Environmental Defense Fund, which they founded the next year. That looks like it'd be very interesting. The Endangered Species Act. When Congress passed it, they recognized our rich natural heritage is of aesthetic, ecological, educational, recreational, and scientific value. Okay? So these all came directly out of Earth Day, and that's what we're here to celebrate. This is a very positive message of how we deal with the Earth and how we deal with our environment. So what happened? Did these work? Look at the George Washington Bridge here in New York City, 1973 to 2001. I'd say that's an improvement. West Coast, Los Angeles, much, much better. I was there a couple years ago. I'd gone to school there, but I hadn't been back in the summer for a long time, and I was there one day in the summer having lunch with a friend outside, and it was literally 100 degrees Fahrenheit. Very hot day, but okay, we're in the shade. I'm looking, I can see the mountains, and I'm asking him, going, what's going on? Is there some weird weather event going on? And he looks at me like, well, it's like this every day. I said, but you can see the mountains, because I was used to this, where you couldn't see anything. I mean, you wouldn't be able to see the stack from here on a hazy day. It would just kind of a white sky, and that would be it. So it really cleaned up the atmosphere. Some statistics. Vehicle miles, increase of 200%, meaning we're driving, this is California, 40 years here, percent change. 200% increase, meaning there's 3 times the number of vehicle miles, 2.5 times the number of vehicles, twice the population, and our pollutants, sulfur dioxide down about 95%, nitrogen dioxide down about 70%, carbon monoxide down about 95%. This is remarkable. This is a 7.5% a year decrease, meaning this is a scale to look at. If I start up here at about 100, from 1960 to 2010, I'm down about here at about 2%. There's been a 98% reduction. These are all various organics, auto exhaust factories, and so forth. Southern California Air Control Basin, kind of the same pattern, some not as much as others, but 100 down to, that's a 60% reduction of NOx in the worst case. The pan, which is an organic chemical, it tears your eyes, it's horrible to have, is down by even more than that. That's down more than 99%. This is successful, this is good. US overall, this was just California, but the US overall, these are statistics from the EPA. We've gone from 1 trillion to 3 trillion miles traveled, and our emissions are dropping 95% or more. Okay? Lead, we've taken lead out of gasoline. This is in the last 35 years or so. Lead has dropped 98%. Carbon monoxide, 85%. Sulfur dioxide, 80%. Nitrogen dioxide, 60%. Ozone, 33%. This is across the US. The Dow Jones during that time doesn't seem to be any big drops, and these can't be attributed to any of the regulations we did. So we've done this without crushing the economy. This is a smiley face. Earth Day is good. Let's all clap for Earth Day. Earth Day did it, okay? It was a wonderful thing, and everybody got together and made changes. How do the rivers look? The rivers are much better. The Cuyahoga represents a tremendous success in individual effort, community resolve, and national public policy. The rivers still have issues. A lot of it is legacy infrastructure. They had raw sewage from all the villages upstream running directly into it. And even though they've stopped that, they haven't gotten rid of it all. But the rivers are much better. Potomac is cleaner than it's been in decades. And now the important, okay, that's it's supposed to be a smilier face. The birds, the most important thing. The robins, Rachel Carson thought they were going to go extinct. Over 300 million of them. They're pretty much a North American bird, over 300 million. The bald eagle, this is a picture my friend and colleague Steve took on the Forge River last year. This is a bald eagle raising a young on Long Island. There were 5 nests on Long Island last year. 50 years ago, there was 1 in the state of New York, and now there's 5 nests on Long Island. They've been seen at the lab. I saw a pair this weekend out by Flanders. I was driving and looked up and said, those are bald eagles. This is remarkable. If you don't shoot them and don't poison them, they're resilient creatures. Osprey, anybody recognize this? This is a cell tower behind Berkner. They nest there. I saw one there a couple years ago. They've been nesting there for years. Okay? The birds are coming back. This is very good. These are gone. Extinctions forever. We will never have the eastern race of peregrine falcon again. We've reintroduced others into this habitat. There are peregrines on Long Island, but that race is totally gone. Okay, so we went back 50 years. We had some, what at the time seemed insurmountable, massive problems with our air, our water, the other creatures. But we solved them. We solved them, and we continue to live the lifestyle we do. Our GDP has grown, the Dow Jones has gone up, life is good. What about today? Well, we have another set of issues today. And I'm an atmospheric scientist, so wherever I go, the first question is, the elephant in the room, okay, is there global warming? And I try to avoid these discussions because most people don't want to listen. They want to tell you that what they heard on one or the other TV shows or read somewhere, and I try to avoid them, but I can't always. But here it's important to talk about. So as a scientist, I say, well, it's not really global warming. What we want to ask about is climate change, because global warming is the rise of the temperature. That's just one aspect of climate change. And it's really not climate change we want to talk about. It's anthropogenic climate change, meaning are we as a species doing something to change the climate? So I researched this. I tried very hard to be accurate in everything I put here. And in any language, the answer is yes. There's no scientific debate about this in my mind. Scientific questions are how fast is this occurring? How severe is it going to be? What are the feedbacks and so forth? You go to the scientific conferences and there is not like you see on TV where one sits up and says yes and the other stands up and says no. It's all pretty much one way. And this is a quote I found on the web, of course. Everything's on the web. The risk of climate change is clear. The risk warrants action. Increasing carbon emissions in the atmosphere are having a warming effect, and I'll talk about why that is in a bit. There is broad scientific and policy consensus that action must be taken to further quantify and identify these risks, assess these risks. So lest you think I took this from some science website, this was from ExxonMobil's webpage. You can go to Chevron, you can go to BP, you can find the same thing on any of their web pages. The oil companies know this is happening. If you don't believe the oil companies, maybe you'll believe National Academy of Sciences, NASA, American Geophysical Union, American Physical Society, American Meteorological Society. I could have pages of this. They've all issued statements saying, yes, there is anthropogenic climate change. It's caused by us. Department of Defense gave a report to Congress last year, and they talked about this and said, reality of climate change, they recognize that. They said they see it as a present security threat, not a long-term threat. Already observing the impacts. This just came, Davos, Switzerland, the World Economic Forum. 750 economists were surveyed earlier this year, and they said the number one risk with the greatest potential impact this year, ahead of weapons of mass destruction, ahead of large-scale voluntary migration, ahead of all these, the failure of climate change mitigation and adaptation. So this is kind of universally accepted that this is a real issue, and what you hear on the news that might say otherwise is probably not an accurate assessment. I'm sorry. So what is climate change? Well, global warming. Here's the graph that shows it. These are average temperatures around the world from Berkeley, Earth, which is a science place that does it, NASA's, NOAA's, anybody that does this, it's all going to look the same. I just found this graph. And this is an anomaly. Everything's given in anomalies, which is a difference from the average. So we take this 1940 to 1980 as the average and call that 0. And since then, in the last 30 years, the average temperature of the Earth has gone up about 0.8 degrees centigrade, almost 1.5 degrees Fahrenheit. Before that, from the industrial era, starting when we started impacting the environment, we were down about -0.4. So in the last 150 years, we've gone from about -0.4 to about 0.8, 1.2 degrees Celsius, or almost 2 degrees Fahrenheit. And that might not seem like a big deal overall, and in a way it's not, but there's 3 important things to remember from that. I'll get to after this. One more slide. It's increasing. 9 of the hottest 10 years are in the 20th century, and the one before that was, I think, 96 or so. So it's increasing right now. So there's 3 things to remember. 1, this temperature is not uniform around the Earth. It's not that the whole Earth goes up 1 degree. There are winners and losers. Okay, there's a few places that are a little colder than average here and here. There may be a degree below. But look at the Arctic. We're looking at 5 to 12 degrees Celsius, which is 10 to 20 degrees Fahrenheit, warmer than our long-term average. This is the January anomaly. It was the last month they had up there. If I showed you the annual average, it would look identical. If I showed you a 10-year average, the Arctic is warming at a much higher pace than any place else on the Earth. And that has a lot of consequences for ecosystems, for feedbacks. There's a lot of methane in the Arctic. And when we melt the Arctic, the methane comes out, and that's a stronger greenhouse gas, I'll get to what that means in a minute, than CO2. So fisheries, biology, ecosystems, so the Arctic is much warmer than average. The second thing, what's the big deal about a 2 degrees change? Well, there's a lot of regions of the Earth where going from 31 degrees to 33 degrees Fahrenheit makes a huge change in how the world looks. This is highly reflective, it's white, so the energy from the sun that hits that bounces off. This is very dark from space. You see your maps of the blue marble. That means the energy coming from space, from the sun, is absorbed here. So a 1 degree temperature change can make a huge difference. And second, this is our atmosphere. So a 1 degree change this is the amount of heat we've stored in the atmosphere. This is the amount of heat we've stored in the oceans. So the oceans are the big sinks. So even if we curtail our activities now, level off the temperature of the atmosphere, and try to reduce it, we've got this huge thermostat that's going to keep it pretty much what it is. Okay, where does this warming come from? This is greenhouse gas theory. We know this, it comes from increased carbon dioxide emissions. So this is results shown from 1957 up to, I think this was 2014, 2015. Iconic Keeling curve. Any atmospheric scientist worth their salt could stand up and talk for an hour just about this graph. Where are the wiggles? Where do the slopes change? Neat stuff here. Everybody should know what this is, okay? Every student we have, that's the first thing we teach them. So Charles Keeling, during the International Geophysical Year in 1957, went to Mauna Loa, Hawaii, because that's a fairly pristine condition without local interferences, and put an observatory to measure carbon dioxide. And he measured about 315 parts per million. So every million molecules of air, 315 of those are carbon dioxide. Those measurements have been made continuously. He died a few years ago, and his son, who's at Scripps, is continuing these measurements. And now, in the last year or so, we've gone over 400 parts per million. So we know this is carbon dioxide we're putting into the atmosphere because we can do isotopic analysis. We have British coal records. We know how much oil we've produced, and it correlates with this. The wiggles are because there's a lot of trees, and during the summer they draw down carbon dioxide, and during the winter they give it back. So we see the little wiggles every year of about 2 or 3 parts per million. But there's been a steady increase over the last 50 years from about 320 to about 400 parts per million of carbon dioxide. We go to Antarctica. What happens in Antarctica? It snows every year. Air gets trapped in the snow, snows the next year. It's like tree rings, they get packed down. So I could drill an ice core 2 miles down and take it out and count the rings and know what year I'm in. I can extract that gas under vacuum and do analysis to look for carbon dioxide, methane, ethane, all sorts of very cool stuff. So these are 4 different ice cores in Antarctica. This is the Mauna Loa record that we've gotten by atmospheric measurements. These are ice core records going back about over 1,000 years. We were at 280 parts per million until about 1800. We've steadily risen to 1957, and we've got the measurements there. Okay, so for the last 1,000 years, we have more CO2 in the atmosphere than we did before that. Let's go back a little further. Let's take that entire ice core. Goes back 400,000 years, almost 1 million years before now. And we see the carbon dioxide goes between 180 and 280. So what are these zigzags? We're in an ice age, so we have the ice sheet cover most of North America, a lot of Europe and so forth. And when it does that, the water is going from the oceans to the atmosphere. That changes the carbon dioxide. Ice sheet melts, the water goes back into the oceans. So carbon dioxide goes up between 180 and 280, and now it's 400. So whenever I hear, well, it's just a natural fluctuation, I'm going, that doesn't look like a natural fluctuation to me. And where does this come from? This comes from fossil fuel. Why do we call it fossil fuel? Well, there's fossil fuel, and there's what we call biofuel. If I go chop down a tree and burn it, that's new fuel. That carbon is fairly recent. And carbon has a couple of isotopes. It has carbon-14 and carbon-12. Those are the main ones. Carbon-14 is radioactive. Every living organism takes up the atmospheric ratios of carbon-14 and carbon-12. So if I take my biomaterial and plant it in the ground for a few million years to form coal or oil or gas, the carbon-14 decays and I've got only carbon-12. So I can look at the isotopic signature of this carbon signal over time and know that the fuel that's being added is fossil fuel. Natural gas is mostly methane, that's CH4. Coal is mostly carbon with some organics. Gasoline, you buy octane, that's got 8 carbon atoms. So these are all hydrocarbons. They've got hydrogen and carbon. When we burn them, meaning we oxidize them or add oxygen, we oxidize hydrogen, we get H2O, which is water vapor, okay? That's a greenhouse gas. We get carbon dioxide, CO2, that's a greenhouse gas. Very important point I want to make. Has nothing to do with Nietzsche, but the title of the book I like. I see a lot of people, or hear a lot of people talking about oil and gas as if it were an evil thing. They split the world into good and bad. Oil companies bad, fossil fuel bad, green energy good. And I don't like that way of thinking because I think it obscures the issue. It doesn't lead to a productive discussion. We live the quality of life we do because of fossil fuels. They've allowed us to form an industrial era. We fly to different places, we drive, we do scientific research at a place like this. We learn how to feed the world, we make medical discoveries that save lives, all because of the economy and the fossil fuel economy we live in. We couldn't do that otherwise. I would be willing to bet that almost everybody drove a car here today. I personally like waking up in a heated house and taking a warm shower, getting on an airplane to going to visit my mother once a year or twice a year or whatever. All those would not be possible with whale blubber, which was the previous energy source we had, okay? So oil and coal and fossil fuels aren't intrinsically bad. This has allowed us to live the life we do, but there are consequences with that life, and we have to deal with those in a mature way, and splitting things into good and evil is not going to help on that. That's my personal view on that. A little bit of science, okay? Just a little bit, but everybody should understand how the greenhouse gas works, greenhouse theory. So science is fun, and you scientists will know this, but there might be some in the audience who doesn't. So the first thing is the electromagnetic spectrum. Okay, we know visible light. These are the colors we see of the rainbow. Purple, blue, green. And I'm saying everything on here is one manifestation of the same thing. Radio waves that you hear on the radio, microwaves that cook your food, X-rays, gamma rays that we do research with here. These are all the same thing. These are electromagnetic waves. So it's an electric field that oscillates up and down. The electric field goes up, it goes down, it goes up, it goes down. Perpendicular to that is a magnetic field that goes back and forth. And it all propagates through space at the speed of light. So the only difference is the energy. The higher the energy it is, the faster this switches back and forth. So X-rays have more energy than ultraviolet. Blue has more energy than red. Red has more energy than microwaves. Microwaves have more energy than radio waves. Very simple concept. Our eyes can see just a little bit of this light we call visible light. No surprise there, that's what we have, that's what the sun gives off, so we've adapted to see that. But if our eyes were better or enhanced somehow, we could see this whole spectrum. And that's what we utilize the light source and other tools here for, because they can see in other colors that our eyes aren't able to see in. Everything gives off radiation depending on its temperature. So the sun, which is much hotter than the Earth, gives off rays with higher energy. Most of those are visible, and that's why we can see it, because that's most of the, I call it radiation, it's really light waves coming to Earth. The Earth also emits light, but at a lower energy in the infrared. The sun's hotter than the Earth. The sun's about 10,000 degrees Fahrenheit, roughly. If you've done photography, you know you have the little setting, 6,000, 5,600, that's degrees Celsius. And that's the temperature of the sun's surface. Okay, Earth's energy budget. We're a planet out in space. How do we get our energy? We might think we get it from burning coal or fuel, but if the sun went away, we wouldn't last very long at all. So we're dependent on the sun's energy. So the sun gives off fairly high energy light coming to Earth. It gives it off in all directions. I'm just showing the stuff that comes to Earth. And the Earth, which is at a colder temperature, radiates this light back to space. And they're in a balance. They have been for a long time, on average. But that's not really accurate. We really have an atmosphere and clouds. And clouds are important. Clouds do two things. So clouds reflect some of the incoming solar light, scatter that back to space. We know that because we've seen a picture, the very first picture I showed. We have the Earth, it's blue, but we see these white blobs. So that means the camera up there on the satellite saw light that went from the sun, bounced off the cloud, and went up there. So we're losing that energy. It's not in our climate system. Clouds also block some of the energy going out from Earth. And we know that because on a cloudy night, it's going to be warmer than on a clear night because the clouds absorb that energy and radiate it back down. Okay, so what do greenhouse gases do? Greenhouse gases have no effect on the incoming solar energy. They let it pass right through. But they block some of that going out. So if we're letting the same amount in, but we're capturing some of what's going out, that stays in the system, and that's what's warming us. So that, in a nutshell, is the greenhouse effect. Now, that's not a new scientific theory. That's been known for a long time. Tyndall in 1856 first made measurements of the absorption of heat rays by carbon dioxide. Arrhenius in 1896 had a surprisingly accurate estimate for how the temperature of the Earth would increase with increase in carbon dioxide. But the best description, the one I like, is Chamberlain in 1899. That's over 100 years ago. The function of carbon dioxide. The carbon dioxide and water vapor of the atmosphere have remarkable powers of absorbing heat rays, while oxygen, nitrogen, and argon of the atmosphere possess this power in feeble degrees only. Remember the atmosphere is 79% nitrogen, 20% oxygen, less than 1% argon, and mostly the rest carbon dioxide. It follows that the effect of carbon dioxide and water vapor is to blanket the Earth with a thermally absorbent envelope, just like I showed on the previous slide, thermally absorbent envelope. So carbon dioxide heats the atmosphere. As we heat the atmosphere, we evaporate more water. That's a feedback. Water is a natural substance. It's not something we've added, but it's a strong greenhouse effect. So think of it as a credit card debt. You charge something on your credit card. It's generally not that that's going to make you bankrupt or kill you. It's the interest that continues to compile on that. So the initial charge is what you've bought, and the interest keeps piling up. So I think of water vapor as the interest on the carbon dioxide. It didn't start the cycle, but as I add more carbon dioxide and heat the atmosphere, I get more water vapor, and this is a cycle that continues. This has been known for a long time. I had quotes from the 1890s. 1965 reported the Environmental Pollution Panel for the President's Science Council. Possible effects of increased carbon dioxide. Well, duh, warming, we've been talking about that. But other effects, melting the Antarctic ice cap, rise of sea level, warming of waters, that's going to have a lot of effects on fisheries, on sea ice, increased acidity, and I'll talk about that very briefly. The climatic changes that may be produced by the increased CO2 could be deleterious from the point of view of human beings. I like that because it didn't say good or bad, it just said it might be something that's not going to be the best for what we think it's going to be. Recently, the last week or so, report, 1968, Stanford Research Institute, report to the American Petroleum Institute. They knew 50 years ago that carbon dioxide could be a problem. CO2 and submicrometer particles might be the cause of serious worldwide environmental changes. They're talking about carbon dioxide here. Significant changes, temperature changes, almost certain to occur by the year 2000, possibly climatic changes. No doubt that the potential damage to our environment could be severe, okay? Very recently in the news. Well, as I said, there's going to be more evaporation, so the Great Lakes will be shallower, just one of the consequences. It's going to affect fisheries, it's going to affect coastal transport, but it also means there's more water vapor in the atmosphere. More water vapor in the atmosphere means more severe storms, more heavy storms. Heard on the news yesterday that I think it was Monday, Houston had 15 inches of rain in 24 hours. That's amazing. You're not going to have that in a cold climate because there's not going to be that kind of moisture in the atmosphere. Only in a very warm climate. Hurricanes are driven by energy in the atmosphere. Tornadoes. So, shallower Great Lakes. Glaciers and ice caps source 75% of the world's water. So here's Grinnell Glacier over the last 75 years. Here's Mount Kilimanjaro over 100 years. The blue is where the ice, this computer rendition of where the ice caps were. It's lost 85% of its ice cover in the last 100 years. Muir Glacier in Alaska, in 70 years it's gone from this to this. pictures from the Andes, pretty much all over the world, the story's the same. You might be able to find a glacier that's growing, but the vast majority are going away. This is the Arctic sea ice. September is the end of the summer. It's when the sea ice is at a minimum. When they started doing measurements here in 1980, there were about 7 million square kilometers. Now in September, there's about 4 million. Many of you will see an ice-free Arctic in your lifetime. Okay? There's going to be consequences of that. Polar bear was the first species to be listed on the endangered species list due to climate change. Listed as threatened in 2008. I do not like this picture. I showed it to tell you I do not like it. A lot of people show it. It looks like the polar bear is afraid to go in the water. He's going to drown. Polar bears are essentially marine mammals. They're like whales and dolphins. They're very good in the water. They're not afraid to swim in the Arctic. But what's going to happen is they're not going to be able to get their food. Almost all their diet is seals. Ring seals are the main one. Seals are warm-blooded animals. They're air-breathing. So if the Arctic is covered with ice, the seals make little blowholes, and they come up so they can breathe fresh air. Polar bear waits. As soon as the seal pops up to breathe, polar bear has lunch. Well, if I have water everywhere, the seal can come up anywhere he wants, and the polar bear is not going to be able to feed. So I was very fortunate when I was at oceanography. I was in the Arctic once and got a picture of a polar bear. This is what it looks like. It's white everywhere, and they just find blowholes and wait. Many of you might not be able to have this privilege, so I feel very honored to have seen one. Consequences we might not think of. So this is a picture of NASA, from NASA of the North. The Arctic ice cap is right here. That is ice over water. That's like an ice cube in your glass. If that were to melt completely, nothing would happen with the sea level. Okay, so it's ice on top of water. This is September, so this is the minimum. It'll freeze all along here later in the year, smaller and smaller in the summer, and as years go by, it's getting smaller and smaller. This is Greenland. Greenland is roughly 1 million square miles. It's covered with roughly a mile thick of ice, and when that melts, the world sea level is going to go up by 7 meters or about 24 feet everywhere. That's not going to happen this week or next week. I don't want to play scare tactics, but you can look. This is from the GRACE satellite, NASA satellite, which measures gravity. We're losing 250 billion tons of water a year from Greenland. That's quite a bit. It's melting, and it's hard to put that water back up there. So the sea level is rising. Not a lot yet. I think I have a picture here. Oh, I'll get to it in a minute. 2 weeks ago, last week, Greenland had its first melt day. A melt day is defined when more than, I think, 5% of the surface is melting. The previous record melt day was May 5th. Since the last 35 years or so, they've been taking records. The average melt day is in early June. So 2 months earlier, this much of Greenland was melting, okay? Temperatures were 35 degrees higher than normal. So every time I read the news or I get something on my mail from Science News, it's worse and worse, okay? Greenland ice caps are melting. They're melting faster than they think. West Antarctic ice sheet, which if it melted would cause 11 meters of water around the world, is shrinking. It might be increasing in area, but it's being undercut by warmer waters, so it's less volume. So this is a sea level rise. In millimeters, like I say, it's not a ton, but this is the last 100 years, and it is increasing. So what are the consequences of this? Well, look at LaGuardia. 1 meter is going to make a huge difference here at LaGuardia. When you fly in there, you're going, gee, are we going to hit land or are we going to hit water here? This is our study from University of Arizona. This is 6 meter sea level rise. This is 1 meter sea level rise. Kind of busy. I wasn't able to pick up things. But if I go up 1 meter sea level rise, which is about like so, not much in Boston, 7% in New York, 9% in Norfolk, 18% of Miami, 15% of Tampa, 91% of New Orleans. If Greenland melts and I've got more than 6 meters here, 34% of New York, a third of Boston, Norfolk's gone, Miami's gone, Savannah's gone, New Orleans is gone, Jacksonville and Tampa are half gone. We also saw a storm surge from Sandy a couple years ago that showed how many low-lying areas we have on Long Island and Queens and Staten Island. So just a little bit of sea level rise makes all those more vulnerable. It's an artist's rendition of 4 meters of sea level rise. This is Boston. Okay, with 4 meters of sea level rise. This is San Francisco. Okay, so when I have friends that go, well, once that starts happening, we'll deal with it. We'll build a wall. We'll engineer our way out of it. I'm thinking, gee, that's going to be a challenge. I drive to the North Fork to take the ferry quite a bit. Every time I drive out there, I play this little game going, okay, where I am right now, if the sea level went up 1 meter or 2 meters or 3 meters, could I drive this road? And it dawned on me, if the sea level goes up very much, we're going to have Orient Island, Greenpoint Island, Montauk Island, Hampton Island, Fire Island's gone. A lot of this area is gone. So this is going to hit locally and close to home. And again, I'm not trying to play scare tactics. This isn't going to happen maybe in your lifetime. But there's kind of a one-way path toward this. Other possible effects we haven't thought of. Warmer temperatures, meaning animals can move into places they weren't before. The southern pine beetle made it to New Jersey in 2010. Since then, it's infected 50,000 acres. So we put it on Long Island in fall of 2014, meaning this is its second growing season. It's had one growing season. Already infected over 1,000 acres. They've already cut more than 8,000 trees. This is a picture of Connecticut. 80% of the trees affected during the first season. This is a map from last year. The red are showing definitives. The yellows are showing probables. Okay? This is starting the second season of this. We're in the Pine Barrens. Pitch pine is the dominant tree here. Okay, switch a little bit. We've looked at the air. Carbon dioxide in the air, there's going to be a lot of effects for that. Let's look at the ocean, the seawater. As Steve mentioned, I used to work in the CO2 system in the seawater. I'd go on cruises, would measure pH and alkalinity and all the CO2 stuff. You don't have to know chemistry. Basically, I've got carbon dioxide in a gas phase in the atmosphere, and some of it's going to dissolve in an aqueous phase, meaning in the water. Second line, carbon dioxide in water, it dissociates, and I get bicarbonate and a hydrogen ion, and then the bicarbonate will dissociate. I get another hydrogen ion and carbonate. So the bottom line is more carbon dioxide in the atmosphere, more hydrogen ions, meaning a lower pH in the ocean. These are measurements with 7 different long-term reporting sites that go out and do the same transect year after year, measuring pH over the last 30 years or so. The pH has dropped by about 0.1 in the surface oceans around the world. That's 25% in hydrogen ions increase due to our activities as humans. We have impacted the ocean chemistry. That to me is just amazing because it's a big ocean if you've been out there. We have changed it. Well, if I have more acidic environment, what's it going to do? We've all had the experiment where I get vinegar and I get my baking soda and I pour on there and it fizzes. We're dissolving calcium carbonate, meaning coral reefs. The world has effectively lost 19% of the original area of coral reefs. 15% are seriously threatened in the next 10 to 20 years, 20% under loss in the next 20 to 40 years. This year there's an El Nino, which means a lot of heat stress for the coral. NOAA projects that 38% of the world's coral reefs will be hit by coral bleaching by the end of this year. That's 5,000 square miles of coral reefs. But that's not really what concerns me the most. This is a picture of Gulf of Alaska from a NASA satellite, and this is an algae bloom. Phytoplankton, meaning algae, in the oceans account for half the photosynthesis on the planet. That's our life. Without photosynthesis, we have no food supply. Half of it's in the oceans. A dominant source is coccolithophores. These are single-celled organisms surrounded by, guess what? Calcium carbonate. Okay? So if we make the ocean more acidic, we could be impacting the food chain from the very basis. And that concerns me somewhat. Okay, we've talked about the atmosphere. We've talked about the ocean. Let's talk about our interactions with the rest of the environment, the other inhabitants. Geologists and biologists are talking about a 6 major extinction. In the geological record, there have been 5 major extinctions. The last one was at the end of the Cretaceous. The KT boundary is when the dinosaurs went extinct because the meteor hit. We're looking at another one. Species are going extinct in the last 100 or 200 years faster than they have any time in the last 600 million years except for these 5 times. Some you might not think about. The monarch butterfly. These were the abundant ones we always see. Everybody's, oh, I saw that last year. I'd be willing to bet you didn't see one last fall. So look at the population of monarchs. The winning areas dropped by 95%. Monarch counts have dropped by about the same. And the U.S. Fish and Wildlife Service has been petitioned to list monarch butterflies as endangered species. Why did the population drop? I can only speculate. I haven't heard any definitive answers. Probably a combination of habitat loss, probably a large component due to pesticides. But you're a scientist. Let's say I write a proposal that says, I want to study the biochemistry of the most abundant thing out there, monarch butterflies, so that if the population crashes in 20 years, I'll know what it was due to. You're probably not going to get that funded. Nobody cares until we wake up and go, wow, look at these numbers here. Look at these numbers. So monarchs are in serious trouble. Hopefully they'll rebound. Hopefully it was a pesticide that is now out of the system and they'll come back, but their numbers are pretty low. Remember Long Island lobsters? Everybody remember this about 10 years ago? This is the tons of catch for Long Island lobsters. It went from 4,000 tons. I just went to DEC and got the last 20 years of data. 4,000 tons down to a few hundred. Okay. Coincidentally, about the time they started spraying for West Nile, runs into the sound. I don't know that's the case. I'm not making that, but that's a possibility. And again, this is a consequence. Spraying for West Nile is not a bad thing, okay? But there might be consequences to it that we didn't fully appreciate. Another bird, of course, white-rumped vulture. This used to be the most abundant raptor on the planet, 80 million of them. And I know what you're thinking. Yeah, it's an ugly vulture. Okay, fine. But today there's several thousand. They're probably going to go extinct because of this chemical, which was supposed to be benign, but it affects their renal functions and their liver functions, and they die from this. So they've lost 99.9% of their population. And you're probably thinking, so what? But let's step back and go, okay, if I've got 80 million vultures, what do they feed on? And just because I get rid of the vultures, the food's not going to go away. That's a lot of dead things laying around. So what takes up the slack here? There's an extra 6 million dogs in India since this happened. There's an extra 40 million dog bites, and an extra 50,000 people died of rabies because of this. So there are consequences to our actions down the line that we might not initially comprehend or realize when we do this. So we look at something like the turkey vulture, common here. They can eat meat that's infected with anthrax with no ill effects. We could learn something from that. We don't want to get rid of this biodiversity here because there could be benefits from that. So things look kind of gloom today, right? We've been there in the past, but things look gloom today. It's not all bad. If we warm, we can grow wine in Quebec. Growing seasons are going to be longer. It's going to be warmer. Well, some people argue that, we have longer growing seasons, we can grow more food. This is not a bad thing. And it might not be, but my thought is, okay, we look at something like the light source 2. And let's say I went to the control room and started flipping switches and didn't really know what I was doing, and somebody goes, wait a minute, stop. This is a very complicated instrument. You don't know what you're doing. I'm like, yeah, but I might make some parts of it work better, which is true, but I'm not sure that's an experiment I want to do. And I would claim that the climate system is probably at least as complicated as a light source, and we're flipping some switches without fully realizing the consequences of this, and there could be some trickle-down effects like we've seen that might be kind of serious on this. So we're the first generation to feel the sting of climate change, but we're kind of the last generation that can do anything about it. I look at the world energy consumption. Natural gas, that's a fossil fuel. Oil, coal, that's almost the whole bit. I look at the rise of increase and go, this is a problem that's going to be with us. We're not going to get off of this fossil fuel right away. It's going to be an ongoing problem, so how do we deal with this? Well, it's not all negative. We are doing some things. We're doing some things at the lab, so a brief positive moment. We look at price per kilowatt, dollars per kilowatt, or dollars per watt. In the last 10 years, it's dropped from 8 down to less than 3, factor of 3. Look at installations of solar. They're going way high. There's a 32 megawatt solar array just not even a mile down the road from here, Brookhaven National Lab. A little plug for my department. We talked about clouds earlier. Clouds are very important. They have these effects of scattering the incoming solar light, trapping the outgoing Earth's energy. How do they behave when I warm the climate? Well, we need good measurements to make our computer models to make policy, and that's what my department does. Andy, principal investigator for a study called Ricoro. In 2009, he had 5 months of aircraft flights. This is the first long-term cloud study by aircraft over Oklahoma, sponsored by the Atmospheric Radiation Measurement Program, Department of Energy. Andy was the principal investigator. So we're measuring clouds in great detail, thicknesses, abundances, size of the drops in the clouds, all this stuff. 2 years later, Mike Jensen here at Brookhaven, Scott's at Brookhaven, Pavlos at Brookhaven, Stony Brook, and a colleague at PNNL, Pacific Northwest National Lab. Went to the same place in Oklahoma looking at deep convective clouds, MC3E. Deep convective clouds are the ones with huge energy that just, if you see one of those, you figure it's going to start raining pretty good in a minute. Okay, so they had 15 radars. They launched over 1,400 weather balloons. We're out in the field making measurements of clouds. Larry Kleiman, Art Sedlacek, my colleagues, Atmospheric Department, did a study 2 years ago, I think it was, 2013, where they had 60 days in Washington State flying through forest fires. This is essentially a cloud, but they're studying the particles and emissions coming out of it, because these particles are going to affect cloud formation. They also went to Tennessee after that and did prescribed crop burns. They would just fly around and look for some farmer burning his crop, whether it be corn, sorghum, cotton, anything like that, and fly through trying to get certain signatures of what the particulates look like coming from different types of fires. We build mobile observatories. So I got my picture in here, although I had nothing to do with it. So lucky me, but this is a group, people I work with, and they build these. This is a 20-foot van. It's got an aerosol stack on top to draw air. It's outfitted fully with instruments inside. There was a video that came out about a month ago. It should be on the website. Pretty neat. They can ship this anywhere in the world. There's a couple in Oklahoma. There's one going up to the Arctic. There's one in Antarctica. There's one on Ascension Island. So they build these things, and they can turn them on and off in their lab and do all this amazing stuff. They're pretty awesome. I was in charge, as Steve mentioned, of this project called Magic. So there's me with my balloon on the Horizon Spirit. I'd like to thank Horizon. They're generous to beyond and above. This is a ship that goes back and forth to Hawaii every 2 weeks. These are back of a semi, each one of these, and they let us put 3 radars, had 2 technicians living on the ship. We launched over 550 weather balloons, trying to study clouds over the northern Pacific, because making marine measurements is a lot harder than making measurements over land. So these are some of the things we do in our group. I'd fly out to Los Angeles, stay in a really swanky hotel, had a bath in there. Travel first class at Brookhaven, I'm telling you. Okay. So now we're back to today. We went 50 years ago. We saw we had some serious problems, but to a large degree, we resolved them. Now we've got some other serious problems, and every time you have a problem, it looks insurmountable. The problems 50 years ago, looking back, yeah, that was regional. That was the US. That wasn't the whole world. This is global warming. So what do we do? And that's a tough one. And again, I wish I had great answers for you. So the best quote I could find was attributed to Abraham Lincoln, but of course he never said it. Dennis Gabor did. He won the Nobel Prize for holography, and he said, "The future cannot be predicted, but futures can be invented." So the question is, what type of future are we going to invent for ourselves? With that, I thank you. Are you gonna, I guess we'll take questions. I don't know if you want to moderate those, Tom?
Yeah.
Okay. If there's any questions.
We're a little bit over, so we don't have a lot of time. Let's just take a couple of questions quickly. Okay, please.
So I was interested in the oscillations in the CO2 graph. You mentioned that they were because trees take carbon in the summer and release it in the winter. Is that primarily trees in the northern hemisphere or the southern hemisphere? Or do the oscillations vary if you make measurements in Chile?
Excellent question, very insightful. So the questions were, I had said these oscillations were, these oscillations were from the trees and then taking up carbon dioxide in the summer, giving off carbon dioxide in the winter. Mauna Loa is in the northern hemisphere. If you look at a map of the Earth and flatten it out, the majority of the industrial emissions and population are in the northern hemisphere, but the majority of trees are also. And if you plot the same record from Australia on here, the oscillations go the other way. So in the southern hemisphere, it's exactly the opposite. The signal's going to be a little bit weaker because there's fewer trees in the southern hemisphere. But that's exactly a very good point. So in the northern hemisphere, the oscillations go this way, and what Charles David Keeling's son Ralph has done is plot the oxygen to nitrogen ratio. He made some very delicate instruments to do this, and it oscillates exactly out of phase also. So as carbon dioxide goes up, you see a little dip in the oxygen the same way. But the southern hemisphere, and if you were good, which I'm not, you could figure it out just from seeing it. But if I were to plot the southern hemisphere on here, it would be out of phase with this because the trees are behaving separately. Very good question.
Okay, one more, and then anybody who wants to ask more questions, we have beer and wine out afterwards in the lobby, and you can grab Ernie and talk to him then, please. So one more question. Back here, please.
So, I have sort of more of a policy kind of question. So you were talking about, in the first part of your talk, you were giving the motivation for things like the Clean Air Act and the Clean Water Act. And those were very pressing issues in the day, and our policymakers reacted and did those things. And you see then, time goes by, the effect that prompted them is no longer there, and they seem somehow less necessary, less pressing. And you don't only see this in like these sorts of physical science issues. I mean, you could say the same thing happened with something like Glass-Steagall or policies surrounding like the pertussis vaccine. So how do you keep issues relevant to our policymakers when the thing that drove them is decades in the past?
Well, if I understand correctly, okay, let me back up. I would think that the Clean Air Act is something that has has kept going and that has been very good. I mean, we have clean air. Emissions are still going down because of in automakers and so forth. How do you keep it currently in the front of politicians' mind? I'm not sure with the Clean Air Act and Clean Water Act we have to, because now we've grown up as a culture saying we demand clean air, we demand clean water, we like endangered species. I think there's...
No, but we also demand lower regulation on industry. And part of the regulation on industry is the result of clean air and clean water. And if we're going to roll back regulation on industry, we're going to roll back the effects of the Clean Air and Clean Water Act.
Very good point. So there's constantly parties that, for whatever reason, clearly economic, most of this is economic driven, don't want the same regulations. They say it's not a problem, it's not going to be a problem, we can, deregulate, we can cut back. How do we keep that in the front of politicians' minds? I would say doing what we're doing with Earth Day celebrations to the lab, voting, clearly making it known that we demand clean air, we demand clean water. Visit your wildlife refuges, go out in nature, make an activity there, join organizations that have lobbying effects on that. I mean, that's not a scientific answer, that's just my best answer. So yes, it's easy to lose track of that and say we've cleaned up things, and then it kind of slips away and we don't want to do that. I don't have good answers for that. I really wish I did, believe me. Sorry if I'm not answering your question. I tried to address it the best I could.
Let's thank Ernie for a wonderful